And we have a team of researchers there, and my colleagues Javier, Philip, and David Gomez, who are here. They are part of that research. Javier will be giving the next talk. Intel says I'm supposed to show you this, so here we go. So just to get into what is probabilistic computing, I'm guessing given the audience, most of you are familiar with it, but at a very high level, the idea is that if you look at the AI systems of today, they're progressing pretty rapidly, and the first components of an AI systems are typically like sensing and perception. And in the areas of sensing and perception, as we have seen today, and most of you may know, the deep learning approaches have given like beyond state of the art and outstanding performances compared to more traditional approaches. But the thing is, AI systems are expected to process natural data, audio, images, text, speech. And the thing with natural data is it has uncertainty inherently built into it. And so when you look at the sort of next step of processing beyond perception, if you look at things like prediction, reasoning, deciding which action to take, in order to accomplish those properly, we must have a sense of the uncertainty associated with the various events and outcomes. And so what probabilistic computing really is a means of incorporating these uncertainties into our processing and computations by explicitly representing the various variables and system parameters by probability distributions. So instead of having just like single point values for parameters and inputs and outputs, we will have probability distributions for some or all of them. And so, as you can imagine, this results in challenges because now instead of dealing with single point values, you have a vector probably describing the probability distribution. The distributions themselves tend to get intractable very easily for real-world large-scale problems, and so trying to apply exact inference techniques becomes infeasible very quickly. So you have to resort to like approximate inference techniques. And so this presents challenges in terms of storage and computation, and accomplishing, let's say, real-time performance with current platforms becoming quite a challenge. And again, just to touch on the research we are doing at Intel, so we have these research initiatives which we call Science and Technology Center, and we have one on probabilistic computing. And as you can imagine, at Intel, we are interested not just in the algorithmic aspects of it, but we want to figure out how these probabilistic algorithms impact the platform and the system and the hardware performance. And so the research initiatives that we have actually cover the entire computation stack, all the way from all the way from optimized hardware, going to software frameworks, which include programming languages, runtime, libraries, algorithms, and applications. And so as part of this initiative, we are collaborating with universities. As you can see here, again, the research projects are actually covering the entire probabilistic stack. And we do have an ongoing collaboration with CMAT here with Professor Jean Bernard on this specific project. So coming more to the substance of this presentation is focused on uncertainty estimation in deep networks. And so if you look at the current deep networks, there are some challenges with the current deep networks. And shown here are sort of the three main challenges. The first one is that deep networks, because of their scale and size, for all practical purposes, they operate as black boxes. So it's very hard to understand. Let's say you've trained a deep network for a particular task, detection, classification, whatever, and let's say there is a failure. Now, of course, you can take the failure case and retrain the network, but figuring out why a particular case failed and trying to debug that is virtually impossible. So they're not really explainable, is how we say it. The other thing is, pressing the wrong button. The other thing is problems with reliability. And this specifically comes because, as was explained earlier, the last operation in a deep network, if you want to get like confidence values, is a softmax operation, because softmax scores can be interpreted as a posterior probability score, right? Now, the problem with softmax, which we'll cover, we'll touch upon later in the slides, is that they tend to be overconfident values. So even when the prediction is wrong, the softmax value tends to be pretty high. And so you can see here in this example that it's the same object, a bus, but occurring in a different pose, a pose that the network has not been trained for. And so, it's unfair to expect the network to recognize the object. That's fine if it's going to misclassify it. But the real problem is that it ends up with a really high confidence. And 0.92 is still okay. I mean, there are instances where even for misclassified objects, the softmax probability is like 0.999. And so that's where really the problem is, getting hold of some reliability or uncertainty metrics that can at least help us diagnose when a problem is occurring. The last one is they tend to be highly sensitive. I mean, in some domains, they generalize well. So if you have a train set and you go to a test set, yes, it generalizes well. But if you move away from that and you have samples that are, let's say, out of distribution, or if you have samples that have been specifically constructed to fool the deep network, they can fail, pretty badly. And the example of adversarial attacks is an extreme one because, as was shown earlier, by adding cleverly crafted but very small perturbations, you can cause the network to misclassify. So if you look at these images here, this is showing the application of a segnet on a semantic segmentation task on a self-driving scenario, right, in an autonomous vehicle. So here you can see that this is the image and the pedestrians, the street, and everything has been labeled nicely. But by adding a very small amount of perturbation, which is actually imperceptible to the human eye, the humans have disappeared. And you can imagine that's not good for the self-driving car, right, if the humans disappear this way. So these are sort of the problems that occur with more sort of conventional deep networks. And these should be addressed if they have to be deployed in real-world situations so that they can operate in a safe and robust manner. Oh, by the way, before proceeding, I should say, if you have any questions, sort of, please interrupt me. Yes, please.
Yeah, so about these adversarial attacks.
Yes.
It's fine to say, oh, a tiny change and they disappear, and that's bad, but it's a very specific tiny change that has to occur for this to happen.
Right.
I'm just kind of curious, you're concerned more that somebody some sort of malicious actor would try to manipulate it in this way? And if that's your concern, for an autonomous vehicle, what kind of manipulation are you thinking that they would perform?
Sure. So good question. So adversarial attacks themselves are classified into two categories, black box and white box. White box attacks assume that the attacker has knowledge of the network in terms of its architecture and topology and its parameters, and you specifically make use of those parameters to craft an attack to fool the network. In my personal view, that is not very probable. Black box attacks are more general, so you sort of do the same process, but you don't assume knowledge of any of the network's parameters. And one of the ways in which this is done is you sort of craft an adversarial attack on, let's say, a known topology with known parameters, and then transfer it to other networks and see how successful it is. And those also are shown to be successful, but not as strong as white box attacks. But typically, I think these are really used as mechanisms to prove how a network might break, one, and secondly, they're used to actually figure out how to design, let's say, actual physical perturbations that could be introduced in the scene in order to cause it to break. And so I don't have the examples here, but there are examples in which a speed limit sign where someone has put a small sticker with a very particular pattern on a speed limit sign, and the speed limit sign, instead of being interpreted as 25, which it was supposed to be, gets interpreted as 75. In some cases, it doesn't even get interpreted as a speed limit sign. So they're kind of used as a way to understand how to design physical attacks on these networks. So I don't know if that helps answer. So how can probabilistic methods and having uncertainty quantification help here? Basically, it gives you a method by which you can figure out how confident you are in your outputs and how much to rely on them in further downstream processing. And as I said, obviously they're compute intensive, so that's one of the, let's say, practical or system level challenges that has to be dealt with. And so in our group, we're looking at two approaches, which have been looked even by the community at large. One is modeling the uncertainty in the model itself. So any deep network that you train has something called model uncertainty, which I'll cover very shortly. But there's uncertainty that arises from the distribution of the data itself, and this distribution induces a distribution in the feature space. So we'll kind of look at both methods. At present, we sort of have two parallel research paths on these, but the intent is to come up with a method that actually combines these two in a good way. And so just as an example of how having uncertainty can help, so by the way, this is not an adversarial attack. This was just an image given to a segnet. And as you can see over here, the sidewalk has been classified as a road. Again, a bad thing for an autonomous driving vehicle because we don't want, the vehicle to go over the sidewalk and run over whatever is there, right? But if you start looking at the uncertainty there, you can see, so this is a heat map of uncertainty, and as you can see that the brighter the colors, the higher the uncertainty. So even though the labels don't tell you much, but the uncertainty in this area is high, so at least whatever downstream processing is there that is making use of these labels can use this in some way to figure out that, to take some safe actions. Let's just put it that way. So that's how uncertainty quantification can help. So the first approach which captures model uncertainty is Bayesian deep learning. And what happens here is that instead of a conventional deep neural network whose parameters are represented by just single point values that you get as the outcome of training, each parameter is represented by a probability distribution. So as you can see, that obviously makes the network more complex. And the way these distributions are learned from training is by you first place a prior distribution on them, and then based on the training data, you learn the posterior distributions through the variational inference. I won't get into the details of that. What is really important for this talk is that instead of having just single point values for the weights and biases, you now have distributions on the parameters of the network. Okay, great. But what that means is that during inference, we have to sample from these distributions because there is no single value for the weights and biases. And since this is a distribution, obviously sampling only once is not going to give us the outcome that we desire. So we now have to sample multiple times from the network in order to get an outcome. So that's sort of one, you can say, practical challenge with Bayesian deep networks, that any input has to be processed multiple times. You need to have multiple forward passes at inference. But the benefit is, instead of getting one output, you get a distribution of outputs, which is captured in the form of this predictive distribution. And there's tons of work showing that this can be used to derive uncertainty metrics and predict out of distribution samples and detect adversarial samples. So this is really a really powerful technique in order to capture uncertainty from the model. They're compute intensive. And so I'm showing here the results of applying a Bayesian deep network on an activity classification task. So for this activity classification from video. So for this task, what we had was a 3D ConNet that has been trained to classify activities from the moments in time dataset. This dataset has 108 activity classes. And for the sake of our test, what we did was we trained this ConNet with only 54 of the classes, and we kept the remaining 54 classes as out of distribution classes. So we are not really training to recognize those. Now what happens if you use a conventional neural network and you use just the softmax values, you look at the histograms of these softmax values. So what you see is that the histograms of the in distribution and the out of distribution, so in distribution is in green and out of distribution is in red, these overlap a lot. So basically, by using softmax, it's not going to be possible to detect these out of distribution samples, right? But if you look at a Bayesian deep neural network, you can very easily see that the histograms have been separated to a pretty good extent. Now, this doesn't mean that the Bayesian network will learn to classify out of distribution outputs. It hasn't been trained for that, so obviously it cannot classify that. But at least with the wrong labels, you'll be getting an uncertainty metric, which is strongly indicative of whether this particular outcome is to be trusted or not. And you can kind of see this based on the separation or the lack of overlap between the two histograms, between in and out of distribution samples. Another application where we've used this Bayesian approach is that of multimodal audio, fusion for activity recognition. So here, we're looking not just at video data in order to be able to recognize activities. We're looking at video and audio data. And so here are some examples of what can be happening. So you see here like a child vacuuming. So if the task is vacuuming, both the video and the audio are able to recognize these independently. So you get like low uncertainty in each of them. In this particular task, if you look at bicycling, the audio network recognized it as high uncertainty, but the video one recognized it as low uncertainty. So the architecture here is that we have two separately trained networks, one to recognize activity based on video, one to recognize activity based on audio, and we're going to combine their outputs by using the uncertainty produced by each network. And yeah, that's basically the problem statement. And so here are some of the results. So I'll just go through each of these in turn. So we tried three approaches. One is just a plain deterministic or traditional deep neural network, and two flavors of Bayesian deep neural network, one using something called Monte Carlo dropout and the other called stochastic variational inference. They basically differ in implementation, but the principles behind them are very much the same. So in Monte Carlo dropout, during inference, you actually randomly drop out some of the weights, whereas in stochastic variational inference, you don't do that. You just keep sampling. I mean, at a high level, that's really the difference between these two. And you can kind of see that the accuracy is improving slightly. So there's really not that much gain in accuracy, but you do get a much more meaningful gain if you end up combining the modalities. So if you look at vision only, the accuracy improves by like 0.5, 0.6%. Similarly for the audio, maybe 1% improvement. But if you combine vision and audio, then you see sort of like a 4 to 5% increase in the accuracy. So that's the first thing that tells us is that combining an audio and video is a much better way than relying on individual modalities alone. But if you look at these precision recall curves and ROC curves, that actually gives you an indication that the uncertainty from the Bayesian network is much better than the uncertainty from the deterministic network. So let me explain that. So the precision recall curve, as was explained earlier, it's plotting precision versus recall. And as you'll recall, a higher mean average precision or average precision value or area under the precision recall curve value is preferable. Receiver operating characteristics or ROC is very similar. It plots true positive rate against false positive rate. And again, similar intuition, a higher value is better. It means better separation of the classes. And for our experiments, we just like to test both of them. And so you can see for the conventional methods, the precision recall curves and the ROC curves, which are in blue, kind of significantly lower. Whereas if you start using a Bayesian network, and especially one in which the audio and the visual modalities have been fused using Bayesian uncertainty, then you get like about like a 10 percentage point improvement in the precision recall values, which is pretty significant. So what's that's telling us is that we are able to distinguish between the in distribution and the out of distribution samples, or the true samples and the false samples, much better. We might not be able to classify them better, but we'll get a much better uncertainty metric for them, which would be useful if you start processing them for different reasons down the line. Any questions on these? Okay.
I have a question.
Yes, please.
Regarding the sampling.
Sure.
So when you classify a new sample, you have to do the sampling of parameters, or
Yeah, you have to do the sample from the parameter.
Sample, make a sample and fix the values of the parameters, and then you classify any other sample.
No, so what happens is, let's say you're processing an input image. You'll pass the image through the network, but the network parameters are themselves defined by distributions. They don't have a fixed value, so you have to sample from the distributions in order for the parameters to have a value. No, it's not conditioned on the input. It's just, so they are like posterior distributions, as I showed earlier. Let me go back. Yeah, so these are kind of posterior distributions that are learned from the training set. They are not conditioned on the input. Yeah.
Did you make any assumption in order to simplify the model of the distribution? For example,
Yeah, usually,
of distribution?
yes. So the standard ones are Bernoulli and Gaussian,
Okay.
and we use like mean field inference. So like basically each weight is like a single 1D Gaussian with a mean and variance. But just doing that itself gives you a very sort of good and robust uncertainty metric.
And if instead of running many times
Yeah.
Or simulating the weights of the network,
Yeah.
you use some estimates, for example, the mean of the distribution, it works the same, or
Oh, so you're saying that instead of
running many times and make a type of bolting, I think, at the end of the
Right, so you're saying instead of sampling from the distribution, use the mean of the distribution and run it only once?
Exactly.
Well, so the thing is, if you do that, and we have tried that, that basically becomes a deterministic neural network. And by running it many times is what gives you this predictive distribution, which allows you to extract uncertainty metrics from it. So if you ran it only once, you wouldn't be able to get the distribution at the output at all. So you have to run it many times. So I think your question might be, if you use the mean, would you get an improvement in accuracy maybe?
Exactly.
Yeah, but as you see,
What you lost.
yeah, but see, even running it multiple times didn't really give a great improvement in accuracy. What it helped us with was in getting an uncertainty metric, which can be inferred from the predictive distribution at the output. Sorry, I don't know. Yeah. Okay, I think I'm running over time, right? So let me quickly go through the other method, which is modeling of deep features. And so, as I said, this is based more on modeling the distribution in the input space, which gets transformed into the feature space. And here we use a standard deterministic DNN. There's no distribution on the model parameters itself. And so what we do is we assume that we have a trained network. But what we're going to do is we're going to learn probability distributions at the various features of this deep network. And then at inference time, we're going to basically calculate the likelihood of a test sample with respect to the learned probability distributions. And we'll see how well this works, right? This is just some details of the distribution we tried. And one thing worth mentioning is that what we did find, and sort of what is well known, as that typical real world data has a much lower sort of inherent dimensionality than the size of the input being received. And that's true even for the feature space. So we do have, ideally we should be learning distributions on the manifold, but as a sort of first crude step, we just apply PCA in order to reduce the dimensionality, and that helps quite a lot. And so in this method, the advantage is that you have to do just one forward pass. There's no multiple forward passes. You can apply to networks that have already been pre-trained, so there's no special training mechanism here. And here we are showing how effective it is in detecting adversarial samples in video. This area hasn't been studied a lot. Image adversarial attacks, there's a ton of literature, but on video, there's not too much. So here what happens is you look at this clean image, and there's a type of adversarial attacks known as framing, adversarial framing, where all you do is you add this sort of 4-pixel boundary to the input image, and it's sort of a specifically crafted 4-pixel boundary, but that results in actually pretty significantly bad results. And as you can see here, if the accuracy on the original data for activity classification on this video data set was like 82%, and just by adding this 4-pixel boundary, it dropped to like 3%. So it's pretty significant. And here we show how well the various approaches that we've discussed so far perform. So if you just look at a deterministic deep neural network, where we're using softmax values, actually this graph is the worst, because what is happening, the red samples are the adversarially perturbed samples, and they actually have higher confidence than the true samples. So they're like fooling the network so badly that the network thinks that these are the real samples and this is the adversarial, right? If you use a Bayesian neural network here, that doesn't happen, but you can see the histograms are overlapping to a large degree, and so as a result, it's sort of hard to separate between the two. But if you use this modeling, so this DFM is deep feature modeling, if you use the modeling over the feature space using probability distributions, these histograms are really well separated. And so quickly, if you just look at the area under the curves, whether it's precision recall and ROC, you can see that by using the deep feature modeling methods, you get like really good results. Bayesian neural network gives reasonable results, but kind of lower than deep feature modeling, and softmax just fails completely. I mean, it's unable to distinguish true samples from false samples. I think in the interest of time, I'll skip this. We did the same thing with out of distribution and adversarial detection, even on image data sets, where we tried it on, I'll go over it really quickly, where we tried it on MNIST and CFAR10, and we trained the network with the standard image data set, and to test it, we actually give samples from different data sets. So for MNIST, we'll give it from eMNIST and Fashion MNIST, and we tried the FGSM type of adversarial attack. For CFAR10, we gave samples from SVHN and actually even LSUN, so I should have mentioned that here, the large-scale scene understanding using standard architectures. And first of all, you can see that the classification accuracy doesn't suffer, similar to the Bayesian network, but you get like very good AU ROC, the area under the ROC curve values, all very close to 1, which indicates that it's able to distinguish between the in-distribution samples and the out-of-distribution one. So sorry I had to hurry to that, but that was the last slide.